Hello, can you hear me?
Yes, sir. Does it take time, sir, to start? Hello, sir. Good evening, sir.
Hello, can you hear me? Hello?
Yes, yes, sir. We could hear
Hello
you.
everyone. So let us start for
Can you hear me?
this fourth session. FDP at IIT Guwahati. Myself, Dr. Anshuman Jana, coordinator of this FDP program.
Your voice is not much audible, sir. It is very low voice.
Hello, now is it better?
Yes, sir.
Hello. Hello. Hello, sir. Can I just introduce? Then you can start, sir. Hello. Hello, am I audible?
Yes.
Yes. Sir, just I want to introduce you and then I just to introduce two other participants also, then you can start. On behalf of this FDP program, today our speaker is Professor Bimal Bhatia from IIT Indore. So as myself, Dr. Anshuman Jana from IIT Guwahati as an co-coordinator. Faculty members, research scholars, and master's students across various institutes over India. They join as an FDP program. Around 100 plus participants will join these sessions. And also I will introduce our renowned speaker, Professor Bhatia, to all of you. Sir already is currently working as a professor, a hack with the Indian Institute of Technology at Indore, and he's an adjunct faculty at IIT Delhi, IIT Delhi, India. He received PhD degree from Institute of Digital Communications with this University of Edinburgh, UK, 2005. And also he has lot of experience and vast experience in industry, academics. He has more than 420 peer-reviewed publications, has 16 patent and also more than 27 awarded PhD thesis. Sir has a lot of experience in various field areas, and he also involved various various co-chair sitting members in conferences and many more projects in India and over across globe. And also, sir has been nominated amongst this world top 2% scientists by the Stanford University in 2021, 2022, and 2023. So just I welcome to you, sir, for this FDP program. You enlightened all our participants. So I hope that all participants will get more and more knowledge from you. So thank you, sir. I hand over to Mike to you, and you can start your talk today's session.
Okay, thank you so much, Anshuman, for the introduction. I have my end, and it's good. You have a lot of participants joining in. That's okay. I think we can start, and participants can join in as the session goes.
Yes,
I have got my slides for today's talk in two or three different slide decks. The first one is largely about our research group, what we do. So the participants, be it faculty, student, or research scholars, if they are interested to explore more in those areas, so not specific to the topic today, but largely in the same area of communication. So if they are interested, they can get in touch via email. And we can then discuss what could be the possibilities of joint research or joint thesis or something. So initially, I'll just tell you a brief overview, and then we will look at different types of learnings in which the topic for today is also covered a little bit. And then we'll look at what we did and how we did use the federated learning in our problems in communication systems. Right, so let me first give you an overview of what we do in our research group. So I should have my slide deck open. Put into full screen mode and then we can discuss. Yeah, so let me attach it. Yeah. So my video, but you can see the screen.
Yes, sir. Yes, sir.
And let me change it as well. Let me see if you can change the slides change. You can see.
Yes, sir.
Okay, so let us start. Thanks for inviting me over, and thanks for conducting this FDP, largely the FDP, largely the faculty members here. And it takes a lot of time, effort to plan these things and get all the logistics in place. So thank you so much, and all the best for the future days, coming days as well.
Thank you so much.
So about myself, you're welcome. So myself, Professor Vimal Bhatia, working in the Department of Electrical Engineering, and we also have a small center called Center for Advanced Electronics, an interdisciplinary research center. So where we have people from electrical engineering, of course, also people working on silicon, photonics and those areas. Also people from material science, computer science, mathematics. So they're all part of this interdisciplinary center. And also adjunct faculty with Bharati School of Telecom Technology Management at IIT. Also Drishti, CPS, Cyber Physical System Chair Professor at IIT Indore, and was a former research director with Olu University, and editor, associate editor for a few journals. Some of the group members are mentioned, or not all, to update this list, but these are all the graduated students, largely the PhD students. And I would like to thank our sponsors over the years, largely MIT, Ministry of Electronics and IT in India, Department of Science Technology and SCRB, now ANRF, Ministry of Education. We had external funding from international along with international partners from AKA Finland, TFK Finland, then UK IERI, Indo-US Science Technology Forum, EU, and others. This is a slide that I usually put up when I'm presenting things outside of the country. But again, there might be participants from all over the countries. So here, Indore is somewhere in the center of the country, but more towards Mumbai. So down south from Delhi and inside the country from Mumbai. And we have IIT and IIM both in the same city. So about myself. Did my PhD from Edinburgh in 2006. This is my degree then. I'm doing signal processing from NSUT, formerly DIT, and I've got I've worked in ICT industry both in India and the UK for about 12 years, and now working with Department of Electrical Engineering at IIT Indore since 2013. I think someone is unmuted in the session. If you can maybe mute, and we'll take the question and answers later.
Yes, sir.
Yeah. Also featured in the Stanford University Top 2% centers globally for the last 3 years, and also associated with a startup called VNeural, and we work in AI, ML, and telecom area. And so as as a faculty member, you do a lot of other works as also in part of different committees and stuff. So I think in one of the committees was with director of IIIT Guwahati. I think it was with IIIT Vadodara. We were together in this. So yeah, about our group highlights. So we work largely in performance analysis of beyond 5G, 6G communication systems. My thesis was in adaptive signal processing. You can say it's again the foundational work or similar work as machine learning and now it's deep learning algorithm. So we had applied to communications largely, but there's one application we have done which is biological application. I have one next slide which will give you a little bit of idea. Perhaps some of the participants can get some idea or motivation to work in interdisciplinary area, where we had different institutes with different expertise come together on a societal challenge. We do work in visible light communication systems that will cover day after, and some of the latest things that are happening there. Optical and quantum networks is something that we have done 2 theses on, and this is something that we'll be focusing for the next few years, thanks to our support from the National Quantum Mission on Quantum Communication. So our focus will be on communication aspect. There's a big, some of you may have heard, there's a big initiative by the government, and in the communication aspect, there is a focus to link the country from north to the south, and we are somewhere in the middle, so we are part of this north-south link with the TG group from IIT Madras. We did one thesis on radar signal processing and some solutions for industry and defense. There's some of our partners are from across the world. We were largely external funding from both India and abroad as well. And currently, we are executing projects with the UK, Taiwan, Sweden, and Finland. And these are some of the outcomes from the group. And some of our alumni are faculty members at IIT, NITs, triple ITs, or are doing postdocing or working for industry in the UK. This is the first application where AI, which I said, interdisciplinary work. So look at photonics side. So this was interdisciplinary work where we looked at how we can find out if a seed is viable or not. So rather than farmer finding it after 2-3 months, we can tell in a few hours, if in actually minutes, that it is viable or not. Our focus was largely on soybean seed. We worked on this interdisciplinary area because biology is not my area as such. So we and even in photonics, this kind of setup. So we worked with ITDAVV based in Indore. Also, Soybean Research Center is a central government facility based in Indore. So all 3 of us got together. And we had a few projects, 3 to 4 projects supporting this over 6 to 7 years duration, where we developed a lot of techniques. But this is just showing one aspect where we can work with faculties from different institutes with different expertise coming together for solving a societal problem. A lot of good publication, patents, and even prototype came out from this initiative. The next work that we'll not go much in detail in this FDP, but maybe in the future, it's see if you are from telecom background, and let's say even if you're not, then our telecommunication networks, they are largely split into 2 different classifications we do. So the first one, we call it as an access network, where it is largely wireless. What does that mean is, you have a device that's connecting to a base station or a Wi-Fi modem. So that's network we call as an access network. And then we have a backhaul network. Now, backhaul network is largely an optical network. In fact, even connecting our data centers or huge compute, we use optical fibers connecting cities, connecting intercontinental data fibers. We use fiber optical network. Even it's coming to the homes, it's coming to your campus, and then after that we use a modem to convert from an optical to a wireless domain. So this is very important. So we largely looked again at interdisciplinary work did. It was looking at if there is a disaster or earthquake or there's a cable cut happens, then how can we recover? So largely routing, or you can say resource allocation problem as well. Um, Now did one thesis on this aspect, an extension of the previous work, looking at a quantum key. So we're looking at quantum key secure. So why this is important? Because with the coming of quantum computers, they can break the current encryption in real time. So if you have, we use AES type of algorithms to do encryption. So, let's say you are doing a financial transaction using Paytm or other UPI app, and or even on phone on your internet banking, and if somebody can decode that information in real time and even fudge that information, then there's a big and same thing for the defense as well. So for defense, government, and financial services, this is very important to have a secure network. And quantum key, distribution is you can say it's low hanging fruit because when the concept things started very early. Hello. Okay, so I'll continue. Yeah. So we started on this very early. There are already headways made by companies in India as well. So CDOT, being a government organization, and then private on like UNIU Labs and others, they have already made products for quantum secure optical networks, and there's a continuous R&D that's going on. But this is something where we have some products available that we can build on and use. So if you look at this figure here, we have additional data channel which is already existing in the optical networks. Then we have public interaction channel that's used largely for signaling purpose. That's used similar to the wireless signaling channel. And then there's a new channel that is introduced. That's called as a quantum signaling channel. So our focus here is that this channel, quantum signal channel, is able to is secure, and the current optical infrastructure can be used. So we are already executed one project, two and three are just starting. So this is a very active area of our research, collaborative research. Now, this is the topic for today. We'll go much deeper into it later. So now I'm just giving you an overview. So we looked at algorithms for MEC. That's where FL was used by us. MEC, yeah, we can for mobile edge computing, but mobile edge caching is one part of it, as an important part of it. Basically, if you look at the evolution of wireless networks, till 4G, we had one base station, and from that base station, we call it as a macro base station. It will serve on a mobile tower that you see. So that's serving a few kilometers, and the users within the same few kilometers. Now, from 5G onwards, and the same thing is expected in 6G as well to continue, we have a multi-tier network. We have a heterogeneous network where there's a macro base station and a femto base station or a pico base station. So these small base stations, we call them small because they have a limited capability. So in this world, you can think of it as you have a macro base station and then you have Wi-Fi modems. So Wi-Fi modems, if let's say they are from the same provider, and you have a seamless handover that happens, and they can collaborate and do user offloading and stuff. So here in this work, our focus was to look at a small base station. Small base station have a smaller cache, smaller compute. It can do a smaller power budget. So within that budget, it has to optimize. And the focus here was, we are doing caching. So caching has been there in the computer science world for many years. In our laptops, handset, data is all is cached. But it is different, and the challenge is different for the wireless edge caching. Simply, the wireless channel is very harsh, so people are moving. Whereas in case of computer networks, it is largely, it is static. You connect your desktop or laptop to the optical fiber, and you're just, sitting in the same place. Here, the users are moving, and the channel is harsh. You might be, one point behind a building. You might be sitting in a train or a car. It is moving. You might have signals. You might have interference. So a lot of things can go wrong, and there's a lot of harshness in the channel. And then if you look at the base station, small base station, they have smaller memory, they have small compute. So our focus here was, if we can somehow, using some algorithms, some heuristics, we can cache the content, we can bring the content closer to the user. Then when, let's say, you request for a content, the request doesn't go up to the CDN and then comes back. So for example, let's say you want to watch a Netflix film, which is hosted in the US. So it has to be fetched from US and then played back to you here in India, right? But if we can pre-fetch some of this content, maybe not the full file, because again, the memory is small. So we can pre-fetch some part of the content and then play it back to you as soon as you request. And then the rest of the data can be, or file can be fetched while you are already getting the content played on your handset. So here we looked at various algorithms, we posed certain algorithms and compared with the one that is available in the literature, and we found that our algorithms have a higher average cache hit than the existing algorithms, like last first file. As we do in the caching, right? We always keep some part of the content in the computers or in the computer networks. Now this is an area which will go in detail in the session day after, so I'll skip this one for now. Now this is again showing you that this focus is on NOMA. This is again showing you a heterogeneous network setup, which, as I said, from 5G and onwards, you will see a macro base station, femto base station, or a small base station type of heterogeneous network from the same provider. Now here, if we recall when we are teaching our students, say that yes, you have to go to do a multiple access. So now multiple access, in order to utilize the resources more efficiently, we can do it in time domain, can do multiple access in frequency domain. Right? Now I can give a time slot to each one of the users, or I can give a full frequency, or I can split the frequency for different users. For example, let's say if it's so right, we are given different frequency bands or different radio stations, but at the same time, so at the same time they all are transmitting. But because they're orthogonal, they're not interfering with, or they're sufficiently spaced apart, they're not interfering with each other. However, with coming of IoT type of setup, we get a lot of different users. So with IoT, if you look at in today's world, it's about 12 times more devices that are communicating than the human beings. So that shift has happened with the coming of IoT. Now all these devices have to be connected. They all have different requirements as well. So for example, what happens right now till 4G and even in 5G as well, that we give the users a fixed time and frequency slot. So this resource, time frequency slot, is given to each of the. So let's say I'm a user from Airtel, you're also a user sitting next to me. We both get the same resources for downloading. Let's just focus on downloading only. So then let's say I'm only getting some messages, WhatsApp messages or SMS, whereas when my friend is sitting next to me, looking at a Netflix stream, so his requirement is higher, bandwidth, low latency, right? But then we both get the same resources, right, from the telecom provider, which is not fair. So I'm still paying for what I'm not actually using, but my friend is also paying what he's using more, but maybe he's not able to do more because I'm using some frequency or time slots. So perhaps if we can both do it together access, then both of us gets our more fair allocation can happen. So that's where NOMA comes in, where we are breaking the orthogonality. Now, if we break the orthogonality, yes, we are introducing some interference. Because that's what we were told when that you go orthogonal, be it in time, frequency, or code domain, and that's good for you, right? But then the problem is if you don't do this, then you get interference, right? So now when we get interference, we need to cancel it. In case of NOMA, we are purposely or by design, we are adding interference when we say two users are transmitting at the same time, same frequency. But because it's done in a controlled fashion and based on certain condition, we are able to use some algorithms to cancel the interference. So I can then separate the two users by canceling the interference from from the users and decode their data. This is again not a sci-fi. I think there are already demonstrations available. We have done demonstration in our research lab as well using USRP. So it is there, but it is not added in the standard yet. So maybe later version of 5G or in 6G we hopefully see some version of NOMA being introduced. There are various flavors of NOMA. Our work has largely been on power domain NOMA. Then these are different, let's say, architectures for again future wireless communication systems. Where if we look at 5G, there's a KPI on having a 10 years of battery life. Now, as a common user using our handset, we are connected to 5G, but I have to charge my phone at least once a day, right? That's the case with a lot of us. So the battery technology is not there, and also this requirement KPI is not for all the users. So, for example, if I have a user which is an IoT user, so their requirement is small information that they have to, so small information in kbps that they have to send. In some kbs it has to send, even or in bytes per second. Even it may not be kbps. So let's say you have a temperature sensor or some other humidity sensor in the field, and after let's say 1 hour or once in a day it is sending or twice in a day it's sending information. So it doesn't have to be always on. Right, so there are various techniques that can be used. It can go into deep sleep mode, wake up and then send it, or we can use some kind of energy harvesting power devices. So we can, let's say, use solar or wind power or even RF power. So SWIPE, so simultaneous wireless and information and power transfer, is about using the RF energy which we will use for communication and also for energy harvesting. So here, we have looked at various architectures. I'll not go in detail, but there's a lot of work that's going on in energy harvesting, and that can suffice the requirement for one of the verticals of 5G. Similar, we're expecting for 6G as well. So I'm just quickly skipping these slides. So we looked at various architectures of NOMA and this. They can always be extended for mobile edge caching as well. And this is one book that we came up with recently on 6G for sustainable development for rural and remote community. I guess you are based in an area where rural is not very far from where you are, and also the communities are very remote. So in fact, one of the authors, Sanjram, he is from Manipur, so he could gives and works in the humanities section on human-computer interface. So here we looked at certain solution and possibilities that could be for 6G. Now this completes the first introductory part. Now I'm going to move to some introduction on the different types of learning algorithms, which gives you an introduction to federated learning, and then we look at some advanced applications of it. So So I'm making it full screen, and I'm going to say if you have any question till when I'm attaching while I'm attaching the slide. So please, you can feel free and ask. So let's look at the topic today. So we'll look at introduction to federated learning. So far, the traditional, you see, the machine learning is in a centralized way, right? So we do a centralized machine learning where you see we collect all the data. So traditional machine learning requires centralized data collection. It's processed by a central server, which can become a bottleneck for large-scale implementation in daily life due to privacy concern and others as well. And it also, loads the backbone network where all the data is going. So there's a noticeable performance degradation when the data size becomes larger, and all the data for training is not even utilized. And moreover, some businesses require ML models to respond at a high speed, but that's not possible because all the data has to go to a central place. Learning has to happen at a central place where all the data gets collected, and then it gives some inferences or some solutions are proposed. Now, majority of ML-based algorithms iterate multiple times as well. If you have worked on ML before, so the algorithms will not give you an output in the first iteration itself. You will have to do iteration, you train the algorithms. Even let's say if you're doing unsupervised learning, still you have to have a lot of data processed to do meaningful classification. So that's the problem. So if the data is distributed, then a high amount of data communication is required. So which adds to the power and all the bandwidth requirement as well. It will choke the bandwidth and also the privacy and the security challenges are there. Now there's another challenge is that this makes it as a single point of failure. What it means that all the data is coming to one central place where compute happens, and that's where the if that node fails, then is compromised, then all the information is compromised as well, or learning will not happen. Right? And so that's the problem with the centralized learning approach. Now, this is just an overview of various types of machine learning. So we have the supervised learning. There are different algorithms there, network convolution neural networks, where we initially train the network. So it is a training phase, and after the training phase, we do validation, and then we do the testing phase. There's unsupervised learning. If let's say you're not from the machine learning background, this serves as a quick overview. So unsupervised learning is where you, or in classical signal processing, used to call it as a blind learning, where you learn from the data itself, right? So you don't know anything about the model. You don't know if so let's say you want to do some kind of classification. You don't know if there's a modulation technique. Let's say there's a QPSK or QAM or BPSK is used. But what you do is we look at enough observations, and then you can say, okay, yes, if I'm getting +1 and -1 or plus and minus symbols, then I have enough of them. Then because in communication system and the receiver, it is going to go through the channel impacts will be there. There will be noise. There will be some other nonlinearities and other hardware imperfections. But still, if you can somehow get rid of those and then look at the clouds which are formed, we can then maybe say that it is a BPSK type of thing. So if you see plus and minus of the symbol, or if I see the 4 of those observations, I may say it's maybe QPSK or QAM. But in supervised learning, I've already trained my system with these observations, and that becomes easier because I've already told, oh yeah, there's a QPSK type of modulation scheme that I'm going to get at the receiver. I can do the detection of those. There are only 4 of those possibilities. So this is already a priori information that you have that you can use for supervised learning. And unsupervised, we don't know anything. We learn from the data itself. Now, reinforcement learning is somewhere in the middle. So it has a supervised learning, but it also learns from the environment. So that's called a deep reinforcement learning. So we have some action done on the environment. From the environment, we get a reward. So reward it could be positive or negative. For example, let's say, so this is very much used in, let's say, autonomous vehicle, or let's say you have a small game where you have a maze and you have a small mouse which is trying to find cheese in it. If it finds, if it let's say, if it's in an intersection, it's trying to go right or left. If let's say it goes right and finds cheese, you give a brownie point, you get plus points that it has made a right decision. If in case it takes left and it doesn't find cheese there, or it gets an electric shock there, so we give a negative point there. So in reinforcement learning, we're learning on the fly, and we give a reward for doing a good or a right decision, then give a negative for the wrong decision. So these are largely the 3 main learning ways machine learning or deep learning architectures they work. Now in centralized learning, we have different users. So it could be a laptop, handset, tab, others. So they are all uploading some local data. It goes to a global data source where the global model is trained. Right. So a lot of memory at the global end, and a lot of decisions are done at the global end. Whereas for distributed machine learning, we have a local database. So we have all the users, they have their small database. They also have local models. So it's learning locally, and then it exchanges some model parameters with the global model. So we have a global model as well, but then we have local models too. So from machine learning to distributed machine learning, so unlike in 5G, 6G has prominent features to ensure ubiquitous, seamless, intelligent. So AI is seen as a major enabler for 6G. So for high performance computing, connectivity, networking, and security and privacy protection, thus decentralized ML, in which all the private data is kept in training devices. So I have a handset, all my training data is stored in my handset only, not sent to the central store, right? Or we have so here we are saving on the privacy, and also the amount of data that is sent back to the main central store is also reduced. So there's a less load on the backhaul network. Now, distributed ML refers to a multi-node type of machine learning systems, as we saw before. So we have a handset, a laptop, or multiple of these handsets and multiple laptops. They are designed to improve performance, increase accuracy, and scale to a larger input size. It's increasing the input data for many algorithms, significantly reducing the learning errors, and can often be more effective than a more complex method. And the main idea is to distribute this training across the device. So it's not unlike in centralized machine learning, where all is happening at one server, which has got all the memory and all the data access. It is happening at smaller, and so our handset itself or our laptop itself is already doing some learning and sending only the required information to the central store, where some updates and things will be applied to the global model, and from there, if there's a requirement, some information model changes can be suggested from the global model to the local model. Now, federated learning is a part of a distributed machine learning that further decentralize that way of working. So if I look at the DML, distributed machine learning, we have data manager, we have partitioning of data. There's a model, so small models are here, and this all goes to the model partitioning. Here, in case of basic federated learning, we don't even have this data manager. We're doing it on in the user itself. They have all the data, and then the information goes back to the central store. Now, the major advancements from distributed machine learning to FL to date is FL uses smartphones, tablets, sensors. So in our handsets, there is FL already there. It is in one of the very popular applications. It is there. So FL is working. So this means data does not need to be transferred around the system, and no data manager is required, like in case of DML. Less communication means less risk of data leaks and greater privacy. Unlike DML, which allocates model training to clients in a piecemeal fashion, FL operates in the principle of collaboration, where selected clients will work on the training in parallel. Now, FL also involves less communication DML, which reduces the opportunity for attacks. That's because if you're not, sending your data to a central store or even a central, server, then the data is within your own, device. As soon as it goes out of the device, there's more chances of it being, prone to attacks. Right? So that's what it is, there in FL. So lastly, FL requires dramatically less storage than DML. Where DML framework involves manager that stores entire training set ready to be partitioned for parallel clients, and FL bypasses this problem because the raw data is collected and processed by the client device itself, which has a much local, storage space than getting it to the server. Now there are various forms of it. Synchronous or asynchronous federated learning. That's okay. So synchronous, basically at the same time, they're all devices are learning, and in other cases, asynchronous, they are doing it independently whenever they get. So for example, I have a FL engine working on my handset. So it is working only when it is required. So there's no control as a centralized control that's being given that you do FL, learning at one particular time. But this is going to learn, let's say, when there is let's say, the CPU is available. So at that time, my handset will start to learn its FL model. Now there are various, flavors of it. For the 6G, so secure FL for 6G. So aggregation is very simple operation. So in 6G, we are saying that from 5G we have these three different verticals. In 6G we are looking at local and also hyper-local type of applications, where even the definition of local is even smaller than what was there in the 5G. Then there's a privacy preservation. Now, again, even in 5G, currently privacy is not a major issue or solution, being rolled out. But in 6G, we are saying privacy is an important aspect. Privacy needs to be looked, and trust as well needs to be looked into. There might be some KPIs that may come in 6G. Not sure because it's not come out yet, but there might be some KPIs because the discussions started about more than 6-8 years, around 6 to 7 years ago. So this may come in the privacy case. Here, because again they are learning locally and sending not the data, only the models. So then the privacy is preserved. So there's another application of this FL. For instance, let's say we have different. We want to do some research on the type of data that we get from different hospitals. So different hospitals, they would not like to share an individual's data. But what they can do is, if they have learned from the data, from a patient's data, then they can only send us the models. So those models can then be used for making a global model. So privacy is preserved by design. Same thing for, say, mobile network. So different operators can share their models, not the data, not the individual user's data, and that can help global optimization of the network. No, effective FL for 6G, the long-term goal of human-centric communication 6G is going to be there. Is efficient training can reduce the training time for mobile devices. Data and model parallelization are generally used for to accelerate training and running out multiple machine over multiple processors. FL in mobile edge caching. So edge caching is rapidly increasing. So I'll cover that in detail in the next set of slides. But basically, FL is important. So majority of existing works they do static, but our systems are dynamic. And also, when we look at them, we need to look into non-stationarity and correlation across time. Whereas if you are from a classical signal processing domain, in physical layer, generally we assume like the data to be or signal to be stationary and not correlated. But here it is not the case. The statistics will change, and there is correlation across time. Hence, federated-based caching strategy has been proposed, where caching using the past linear combination of the past caching decisions across time can be used in a different, also in the region and the time. Also, time is also an important as well. Time of day is also important. FL-based caching algorithms are shown to perform better and get a higher hit rate, reduction in delay and energy efficiency as compared to conventional algorithms. Also, when from data privacy point of view, because data is not shared outside the device, it is local. So FL preserves the and also the decisions are made faster, so the quality of user experience increases. We'll look at these different algorithms in detail later. Then there is another type of, let's say, distributed learning is a multi-agent systems, which is used in several examples like traffic control, network packet routing, energy distribution, where it doesn't show the direct implementation of single agent RL cannot suffice. So we use a multi-agent approach for optimal solution, because environment is no longer stationary from the agent's perspective, because the statistics of the data is changing, and that's where this is imperative to use an efficient multi-agent RL algorithm. In general, it is the same as a single agent, but because we use multiple of these agents, they can learn independently and they can learn in a decentralized fashion. Again, this can be used for IoT and other applications. Like we have not explored this, from the research point of view, and also today's topic is largely on the federated learning. So I'll skip this one, but this can be used for for beamforming and other applications. So let me now come back to some of how we applied, how we used federated learning for mobile wireless edge caching. I'll make it full screen, and then we'll link it, right? This control L. Yeah, okay. So let me connect this. Okay, so you can see the next set of slides. Hello, is it the next set of slides visible? Federated learning for base selection. So I'll just, okay, so I'll continue on it. Assume that this is, the slides are changing. And so what has happened over the years is, we see in 2018, the requirement was for, uh, you know, about 28 exabyte of information per month, but this has now increased, and largely it is due to increase in the video consumption. So video part of most online content. So we are watching news, YouTube, videos, social media. It has grown a lot. So growth of video on demand services has increased. Video streaming services has increased, changing user behavior. So we ourselves, can see how we are consuming. So we are consuming, this on WhatsApp and a lot of other models. Actually, WhatsApp, I should have said that, it is one very perfect example where FIL is used, federated learning is used. So it, it. So if you look at, WhatsApp, you are, let's say, using some words or phrases which are not there in the formal language, right? So it is only you use it with your friends, family members or something. So those are, because they're not part of the formal language, they're not learned, or you don't get a suggestion, right? From it. But when you use it quite often, then your local version or model is trained for those words, right? And that's like federated learning for your own uh, device. So those models can then be shared. Only the models can be shared, and those models can be used for updating the global models. Now let's come back to this thing. So yeah, over the years, there has been focus, on video content has increased a lot, and if you look at what was the projection and in 2018 and today, the content is growing very fast. So in India itself, in 3x times, I guess it's now even more than that, about 4x or so from 2018 times. We have been consuming a lot of video content, right? So that requires bandwidth, that requires learning, that requires caching. And the same for consumer customer premise equipment. Also, we are using this even being indoor or outdoor, be it battery powered or not. We are using the data a lot, and this is going to increase for the foreseeable future till 60 and even beyond, because new applications will come in. So there's a paradigm shift. So data traffic from few Gbps to TBS per month for all. So these rates must be a constant rates, low latency jitters, low video disruption, not easy task to achieve. Edge caching in computing has a history. It was earlier than deployed in the content delivery network. So these are like you see, like YouTube as a CDN. You have different TV station, Tata Sky, and their content delivery networks, Netflix, and all. So they would usually have it in their systems, but because a lot of this content is now generated and consumed at the user end in the mobile device, so there is a need for a wireless edge caching. So caching, turning memory into the bandwidth. So on-demand multimedia content has special features. So asynchronous content reuse. Few popular files are accessed at different times. Demand distribution prediction based on user requests and future popularity content can be predicted. Easy to shape demand and distribution by updating cache and refresh frequency. So, for example, you see, for example, let's say there is a cricket match going on, right? And a lot of students are watching it late in the evening, or football match is going on. You're accessing it from your devices while you are in your hostels. So a lot of others will also be watching the same clip, or maybe there's a some maybe the budget session or something else. So that clip may be playing multiple times in the same genre or region at the same time. So then the content can be brought closer to the user by caching it closer to the user, bring the content closer. browser. We can have some refresh rate and all, but the idea is we are doing learning and bringing the content closer so that it doesn't have to go back to the CDN and play it back. So popular files, and also for example, let's say you are a user and every evening, let's say returning to your workplace from your office to your home, you are listening to some type of or watching some type of YouTube video, maybe on sports or current affairs or anything that you are interested in. So then that content can be fetched and brought into the small base station. And now when it's a mobile network, then the users are moving. So here this figure shows that there are users which are connected to different base stations. When they're moving, they keep also connecting to different base stations. Right? The handover happens. So for example, you were downloading some content from, as it shows back, you have a uplink, downlink here, then you have a backhaul connection. From backhaul, you have central router, core router, and origin. So we get this content here. Now, then you have a mobile user terminal here, where the user may move right from connected to one small base station to another small base station. Now, this content has to be then brought to the next base station, or there's a concept which is again not formed into 5G yet. But there's a concept of device-to-device communication. Your friend has a content, right? Correct. Now what happens currently? The content from your friend's handset, it will go from the WhatsApp server. It goes up to the server. So from your say Airtel, you are connected to Airtel. It goes to the WhatsApp server, and then it will be fetched down. And maybe your friend is on Geo network. It goes down through the Geo network, different base stations and core network, and then it gets delivered. But you may be next to each other. Right? So why can't we get the content from one to the next user? Right? Also, maybe the user can work as a relay. So it is connected to the small base station, and where let's say you don't have a good connection, but another user have it, so you can do collaboratively, do a exchange. So it can cache the content for you, right? So the various applications of mobile edge caching, where again the different type of base stations will be used. Could be a macro base station or a millimeter wave small base stations that are there. So here, if we so from this figure, our focus is that we bring the content closer to the user. So for example, a user is a mobile user. It is connected to one base station, and it is moving towards its home, maybe walking. So slowly it will connect to the next base station, and we know that this is the trajectory that the user follows every day. So we can always prefetch some content and put it to the next base station. When the handover happens, the content is fetched from the next base station to the user. Right? Similarly, if let's say people go in a common bus or a car or something, then same formulation can be used, same philosophy can be used. Now, the problem that are commonly addressed in wireless edge caching is the edge caching compared to its counterparts in cloud allows data to be processed in the base station, central store, and other aggregation points on the network. Whereas traditional cloud-based computing works only on the remote device. Right? So wireless edge caching provides computing resources, right? Storage capacity, networking resources, integration with the base station and edge device. So there is if let's say you're working on a base station, it has access to larger memory, or there's a core network, it has access to larger memory, more compute. Whereas this one, a mobile edge caching, a small base station or a handset, we don't have it. Right? So we're bringing the intelligence close to the edge. There's a huge amount of data by devices that can be computed within the edge itself. So not only linked to caching, but also other type of processing can be done. Our focus here has been on caching, so that's why it is largely driven by that. But federated learning is used for other cases as well. So one of the recent cases that we are exploring is doing RF fingerprinting. So we may have sensors at different location, and there might be different SDRs or other type of transmitter receivers used by even let's say for in the border regions we have it may be used by the enemy sources. And they all these radio heads sites, they have a unique fingerprint, so we can try to identify them, and then maybe some classifying can be done. Oh yeah, this might be used from this company, and they might have procured it from a different vendor or something. A lot of this fingerprinting can happen, and that there also we have recently explored using federated learning. So it is not only limited to caching, but because our larger work has been on caching, that's why the focus is on caching. So here this shows the same thing that I've been talking about, that we have a multiple of these small base stations. We have multiple of these users. So n users are there and m small base stations are there. So users are connected to may be connected to multiple of these small base stations, and they may be moving. And each of them, they have some cached content. So cached files, again, because they have limited memory, they can't store all the information, maybe just a few initial seconds before the whole content is fetched from the back. So this is based on a heterogeneous wireless network. We call it heterogeneous because we have a multiple layers. So we have a macro base station and then a small base station. So this content could be fetched from the macro base station, or if it is connected to the optical fiber or IAB type of arrangement, it can prefetch the content. Now here we had looked at SBS and end users. Now there are, let's say, J popular files that are used, so a lot of people will read it. That's why the popularity is high. The storage capacity is, however, limited, so assumed to be not by CM. XJM is showing if it's 0 or 1, if the file is there in the base station or not. So if there is a content in the small base station, then we say it's a cache hit. If it is not, then we say it's a cache miss. Right? So the average rate of cache hit can be given by this formulation. We'll not go in detail, but this then becomes an optimization problem where you can use different algorithms, because your focus here in the design is to increase or have as large average cache hit as possible. Right? So if you have a cache hit, that means the content was already there locally, right? So you win, like a lottery, so it's already there. So, but it will not happen always. But there are again certain algorithms that can be used. So we look at this. It's a NP-hard problem. Not difficult to solve. So where the different algorithms can be used. So I'm just going to skip some of this part. So if you're interested, you can look into the research papers for further details. And this figure just shows the average cache hit rate that we get with cache size for 35 users. So there's 35 users. It is collecting some memory size memory here. And then LFU, LRU, they are traditional algorithms. We compared with greedy algorithms as well. And we see that our proposed algorithm worked better than the one available in the literature. Again, this can be further improved. A lot of DL algorithms based algorithms have come up, so they can also be explored. So we can explore DNN for it. Again, we're not going much in detail, but this figure shows that yes, we can have. So the y-axis got mean squared error, and the x-axis are different algorithms. So there's auto regression, there's GPM, PPM, FTL, DL, and so we see that the mean squared error for DL is pretty low as compared to auto regression and other models for prediction. And then based on the content and the library. So for example, you see in an ideal world, if I had infinite memory, then I could have infinite content being stored locally, even if it's the first few seconds of content. But if I have infinite memory, I can have it all. But that's not physically possible. So we start with a very small memory size, and then we see how the algorithm scales as the memory increases, and also the content. So, for example, this is a library is a fixed size of 500 files. We do a comparison, so cache size keeps on changing. So we compare with the linear model based on auto regression model, and then with the proposed DL model, and we find that the DL model has a higher cache. So you see, even with cache size of 2, we are getting almost 50%, more than 50% times it will hit the right. So we have the right file in our memory. We can use the federated learning based one as well. As I said, it can save, give you privacy along with the learning capabilities. So here the system model mainly consists of a cellular network with M small base stations denoted by the set P and users denoted by the set U. Each small base station is assumed to have a limited computing facility and a small cache size C, which to store popular content. Further, it is assumed that SBS can communicate with each other through limited cables. So what can happen that we have a small base station and you have another small base station. So one small base station can share limited information with the next base station. So why this is important? So to increase the cache, because your user is mobile, right? So you might be connected to one small base station and you moved from your, let's even if it's a straight line, a road, you have one signal and then you get the next traffic signal, your small base station changes. So this small base station can communicate to the next one and can, prefetch and can tell, okay, you prefetch this content because this user is using it. So it will prefetch in memory. And that content, as soon as you get connected, will get played back to you. So as a user, I don't see there is a stop or that the round bit that you see around red one, the circle of depth where the content is being fetched. So it is already prefetched. It's easy to just deliver to the user. Now, a time slot is assumed, and each time slot is assumed to have request contents from content library F having n content, and the demand for content for U in slot T is noted by this function. So this is our setup. We have a common server, and then we have small base stations. These base stations, they have some content that is stored, and there are various users which are connected to these small base. So in this example, there are 5 small base stations, and each one of them, they have 4 or 5 different users connected, and they're mobile users. So we can then have designed some kind of a overall caching policy where again our focus is to increase the instantaneous cache hit. So the online federated learning caching problem is the caching strategy is weighted average of a sequence of caching strategies from the time slot T to time slot T minus tau plus 1. So that we are having this like a regression. So we are having these which are changing. So basically what we say here that the most recent occurrence or learning has a higher weightage than the learning which was a few minutes ago. So or a few while ago or time slots ago. So we give higher weightage to something which is closer. Right, and then we'll not go into detail of the algorithms, but you can look into the manuscript. But basically, we see that there are different things which I calculate. Again, I'm going to skip this part. But if you look at the comparison with the state-of-the-art algorithms, we see that the FL based one, the federated learning based algorithm, works better. The proposed heuristic one is is you see it is um, it knows more than the federated learning algorithm, right? And this is designed with more power. But here we are doing distributed learning, so yes, you will lose some performance, but again, it is still performing better than the one that are existing. But then it has its own advantages that yes, you will have less memory requirement, you will have less compute requirement. But yeah, okay, you may have a lower this than the heuristic based, because there's a lot much more information is known to the heuristic based algorithms. So this is okay for different topologies. One was centralized topology, then the circle one, or a line graph. So let's say you're moving in a line. In that case, the FL algorithm works very well. Also in circle and other topologies too, centralized in topologies too. Then what happens if we change the size, cache size? So if cache size increases, we expect more hit to happen, right? Because initially you had memory which can only support, let's say, 2 files. Then you increase the cache size to 5, 10, 15. So you can have 15 files. So you expect, yeah, more files. So if let's say one of the 15 files is requested, we'll get a hit, right? So that's how we tested. We increase the cache size and see if what is the impact. Now, there is another thing, when we compare these algorithms, we use a data set that's publicly available. We use the movie data set. It is given, released by YouTube. We, in fact, also tried, we have a conference paper on it in NITS. This was with some of the data that we got from our campus. We only looked at the region. Let's say there's a academic block, then there's a hostels, and there's other blocks. What are the most commonly explored content? So we could do this. So there we don't know which user requested what, but what we were looking at is which requests are being made, and we use that data as well to train our algorithm and get some inference. Then of course we can use Bayesian kind of learning as comparison to the federated learning, again in distributed fashion. This should give us a maximum likelihood estimate, because we already have some prior. So problem is to find a caching and a recommendation strategy. So so when you purchase something from Flipkart or Amazon, then they say some users might have purchased X product as well. Maybe you purchase some toys, so they'll say you purchase battery along with it. Or other place where we look at is when you look at some video on YouTube or Netflix, they may say that okay, maybe you're interested in the same genre. They will say okay, maybe this is the next video or something which is more popular, right? So there is a recommendation based system that are also distributedly learned, where we give some recommendation plus the popularity of model that is given. So then you may have a better cache hit at small base station, so it doesn't need to go to the macro base station. So this was the strategy will not go again much into, but the philosophy is yes, you use some caching plus recommendation. That so let's say you watched a comedy from one person, then you may be interested in, let's say, stand up from the same person, or maybe another person, but in the same genre, not completely different. So let's say you looked at some one in, let's say, in Hindi language, so then it will be again in Hindi. So it's not going to be suggesting that you watch English or some other regional languages comedian or something like stand up. So the recommendation will be somewhat similar to what you are looking at. So that's how the systems works. thing it is applied to travel transport and also in other recommendation based systems in let's say you're buying a book, then you may also buy this book or maybe a book cover or something. So these are some recommendations that the sellers of these online stores will tell you. So we'll again, maybe skip this part, not so much in detail. Again, if you're interested, it's already published works. You can have a look at it in details. Then there's another type of criteria that we explored was based on this Whittle index. So that helps in joint estimation of caching and recommendation, and we consider this to be Markov model. So you see, when we okay, let's look at this first. At the end of each time slot, the caching distance associated with two objectives: the reward achieved when the cache file is served to the user, and exploration of the recommendation of a file. So based on Whittle index condition, the Whittle index policy of caching is provided. So when we look at, you see, in a Markov chain, what we look at is you have some content or something that you have seen. The probability of the next one is dependent on the current one, and the current one is dependent on the past one. So it forms a Markov chain, and based on probability. So these probabilities then we can transform to, let's say, probabilities of connecting to the base station, connecting to the type of content that you are using. So there is a Markov chain process statistics that is that is applied. Right? So I'll skip again this part, but this was simplistic. We looked at only 2x2 probability transition matrix, but it can be more and higher dimensional ones. Skip again the algorithm in detail, but if you're interested, you can. So now look at some conclusion. So basically, we say that for a wireless edge caching is one of the important factors. Again, FL and some of the other machine learning tools can be used. That's what we have used even later stage, and not only for caching but also for other applications. And fingerprinting, for other learning, like WhatsApp is using for text. So there's a lot of other applications for federated learning. Future work, we can look at some optimization from. There's a very important concept of age of information. For example, let's say some information is very simplistically, it is important right now. So maybe tomorrow or a month later, it may not be. Right? So you can then ignore that information or something to be shown. So there's a age of information, and again, it is it's a function of time largely. That as the time goes by, that the value of that information is small. So that's what we call as age of information. Or we can even define when we put, let's say, some information on the in the network or in the packet that this information is only valid or important for next 2 days or 2 hours or something can be done. So that's where again the caching algorithms can be improved. Some learning can be improved for those applications. Integrating physical layer parameters, so different types of fading, speed, mobility. We have, you see, the imperfections in hardware. There's channel coding. So a lot of other factors that can be put into caching or in your edge computing or edge selection. So optimizing both energy efficiency and edge caching. There's a lot of algorithms can be given, implementing device-to-device caching. So this is also very interesting. As I said, that if you are transferring some information from someone who's sitting just next to you, so can't you just connect, transfer directly rather than going through the full, mobile chain, right? And it goes to the operator and then to the CDN, and then from CDN it comes down. So what way it is done that way. Some of the publications that will be of interest to you. I can take a snapshot of it. Look at how we look at federated learning used for predicting the correlated demands for caching. Application also for popularity prediction, which is combined with recommendation-based systems, and some important references. So this is not exhaustive list, but yeah, this is one of few you can have a look at. So thank you so much. We can maybe open for question and answers. That's okay.
Thank you very much, sir. So, guys, participant, if you have any questions, you can interact with our speaker. Questions from anybody? Please, you can ask or interact if you have any query, questions with sir.
Thank you, sir. Thank you very much.
Yeah, thank you so much. Yeah, for patiently listening. And yeah, even if there's queries later on, you can drop me a mail or to give a session day after. So yeah, I'll be there. So any queries from this session you can ask there. It's there also.
Okay, sir.
Okay, so then, so thanks to all of you, and I will also thank to our speaker, sir, so for this very nice presentation and very informative presentations and talk. A lot of information we have learned from sir, and also I hope that all participants enjoy and maybe progress in future for all such informations that can be helpful for your upcoming careers development. So I request you, sir, you can share your slide to us so that we can send your slide to all the participants. They can use as a references for their study. And also if any kind of questions come from the participant or any collaborations, so then we will convey the message to you, sir.
Okay, sure. Thank you so much for having me over, and all the best for the future sessions.
Okay, thank you.
Okay. Thank you so much. Yeah.
Thank you, sir.
Bye. Thanks.
Bye. Yes. Okay, so guys, so next session will start. We'll take few minute break. Then our next speaker will join soon. Then we'll start the next sessions. After 5 minutes. Please just take a break for 5 minutes.
Hello. I have already joined the call. Can
Hello.
you hear me?
Yes.
I'm the
You are
presenter for the next session.
Yes, sir. Can we take 1 or 2 minute break for all the participants? Then we can start.
When do you want me to join?
Yes.
In 5 minutes.
Yes.
Can I try to share my screen?
Yes,
so
definitely. Yes, definitely. You can share your screen and then. Yes.
If it's okay. So the voice is okay?
Yes, voice is okay. Fine, perfectly fine.
So can you see my slide?
Yes.
Okay, and can I play back a sound wave just to hear if you can hear it?
Okay.
Can you hear?
Yes, able to hear you. The sound.
Okay.
Yes.
So that's good then.
Yes, good, sir.
So all it's ready then.
Yes, yes.
So I will join back in 5 past or
Sir, maybe you can start within a 5 minutes, just a break of the sessions. So,
so five
with
5 minutes now.
Yes, yes, yes.
Okay. Okay, good. So I'll see you in a bit.
Yes, yes. Hello, I'm audible to all of you. So we'll start the sessions, the second sessions for today. Our speaker will join soon, so we'll start now. Meanwhile, just one notice to all of you, please, you mute yourself once the lectures will be going on.
Okay, sir.
Okay, so many of you actually not muted, that is why background noise coming, so other can disturb and also the speaker can disturb. That is why once you join, you mute yourself. And if you have any questions, query, you can raise your hand and also ask questions to our speaker. And also, I request to all of you be interactive. You may discuss your questions, query, and other stuff if you want with our speakers, so that the speaker will enjoy all the sessions. Whatever if you want to discuss, you can also anyway. So we'll start now. So speaker is going to action, and then I will introduce our speaker, and then we will start very soon.
Can I start the presentation?
Yes, Professor. So just I can just take in 1 minute to introduce from our participant, and also I introduce you to our participant. Then you can start.
Okay, very good.
Yeah. So from this side, all the participants actually been joined over this online mode. They are basically the faculty members, research scholars, and master students across various institutes over India. And also they are been doing this session last 3 days, and this is a 4-day session is going on, and ultimately the program is consists of total 6-day program of faculty development program called FDP. So that is the all about our participant end, and there are from various backgrounds like engineering, science, technology, and all. And all the participants today, our speaker is very academicians and very experienced professors from Nottingham universities, and he has lot of experience in academics over the years. He played important administrative roles, various institutions, and he was a professor of digital communications at Newcastle University. He was head of the intelligence, sensing and communication group between 1722, degree program director of MSc in communication and signal processing between 2003 to 2017, overall MSc program coordinator for all 6 EEE MSc program at Newcastle University between 2010 to 2013. He obtained his MSc PhD degree from Department of Electrical and Electronics Engineering at the University of Newcastle on the trial 1999 and 2002 respectively. He is a member of IET and senior member of IEEE at NQ. He is and currently the lead of digital innovations, research, group at IMEC, Deputy Lead of Engineering Submissions for REF 2000, REF 2029, and Director of Smart Wireless Innovations Facility and Suite. So this is all about our speakers. So sir, I hand over to you the mic and you can start your presentation and enlighten to our participants. Thank you.
Very good. Thank you very much for your introduction. I'll share my screen.
Yes.
And hopefully you can hear me well.
Yes.
So can you see my screen, yeah?
Yes.
Okay, so the topic is related to underwater acoustic communications, and I will provide also some extensions to the quantum relationship. So, right, so if we look at who needs this kind of technology, yeah, so of course the Navy and the military, they're very keen on this technology. Yeah, so you can imagine 2/3 of the world is covered by water. There's a lot of activities by the navies of various countries. So they want to be able to communicate between submarines and research vessels or Navy vessels. So it's important to be able, within the water, to establish communications links. So this is probably the biggest area of application for underwater communications. And then you have the scientific community, oceanographers. They want to do research in underwater. They want to measure things underwater and transmit over time all this data to their office. Offshore industry, oil and gas, of course, they have huge installations around the world, and they want to be able to inspect the installations underwater and eventually get all this information for maintenance purposes or accident preventions. Recently, data centers, so there's some activities from Microsoft and also in China. They have deployed data centers underwater. In the UK, in Scotland, in Orkney Islands, Microsoft has a big research center where they put silos. They put this type of silos inside the ocean, or in this case in the North Sea. The idea behind this is to avoid having excessive cost for cooling the data centers. I think around 40% of the cost of running a data center goes to cooling. So if you put the data center inside the water, you have automatic cooling, so you don't spend any money on cooling. And you can place also the data center near renewable energies like wind turbines and so on, so you can have the local energy and also reduce costs at from the cooling aspect. But once you have them underwater, there's other problems that come about. For example, you have to inspect, the sea is a rough environment, so you have to be able to inspect periodically the structures for integrity and so on. So underwater communications is important in the future for data centers. And then you have other activities like AUV navigation, so remote robotics underwater, and archaeology as well. People want to see all the ancient ruins underwater and study them. And there's also, from the recreational point of view, activities where you want to measure, record stuff and send them back online. And also, very important, the search and rescue operation. So if there's an accident, you want to be able to search underwater. So that's roughly the customer size of the underwater communications. And what kind of data we transmit. So there's two types of data, one which is called the command link type of data. Yeah, so this is very short messages and normally is used to control installations or AUVs. Yeah, AUV is called an unmanned underwater vehicle. So if you want to navigate it, you only need very brief instructions. So typically we call this the downlink, and the requirement is very modest, 100 bits per second, but you want to be able to reach a long distance, so 10 kilometers, that's the kind of range you are looking at. So you want this link to be very reliable, so very high integrity, but the data rate is not really a big problem. And then we have the uplink. Yeah, so this is, we still want to have reliable data transmitted, and the data rate should be a bit higher. But if you use acoustic links, I think the state of the art is around this value, 40 kilobits per second. So if you are in a short distance, around 300 meters. But if you go longer in the distance, then because of the attenuation and other effects that I will discuss, the data rate goes down. So this link is called the uplink and is used for video and sonar images transmission, but also if you collect data underwater and you want to send them to a research vessel or to offshore. So you can use that kind of link to collect the data. And of course, you can also connect instrument data. So this is the kind of type of data people want to transmit in underwater communications. So we have the low rate command links and the high rate uplinks for getting data back to the shore. So in terms of waveforms that you can use, so if you try to use RF communications, you will not go very far. Yeah, as you know, based on the Maxwell's equations, we need the propagation of the E field along with the magnetic field. But because the water is conductive, what you get is the E field is shorted. So the propagation is in the order of a few centimeters if you try to send RF signals underwater. So one way to avoid that is to go down in frequency and increase the wavelength. So if you go down to 30 Hz using these extreme low frequency signals, then you can manage that, and the military is using this kind of link to reach, if you have a station in Antarctic and so on. But what happens is the wavelength becomes very long, 10,000s of kilometers. So it means like to have an efficient antenna in this application would be very impractical. So you will have to spread it across the whole country to reach this kind of antenna size. Yeah, even if you halve it, it's still a significant size. So in the past, people have used for any communications that is at the distance, they have used acoustic waves. So in this case, the speed of propagation is smaller and the wavelength is smaller, so you can create transducers which are more practical for deployment. Yeah, so if you have a transducer which has a produce a wavelength of 50 centimeters, size-wise is a feasible implementation. So in the past, most communications in this area, they have been accomplished using the acoustic wave propagation. Yeah. Within this type of communication, you have typically two channels. One is called the deep water channel. Yeah, so this can go down to 8,000, 9,000 meters, and we call this the deep channel. So this is a very challenging because the equipment that you will use has to be first waterproof for very high depths. Yeah, so it's only reserved for very rich institutions. This kind of communication, so the military, and typically most of the research is done for shallow water type of environments, maybe up to 200 meters. So if you go deeper than 200 meters, then you have this type of phenomenon where the sound propagation is not constant and modulates based on the depth. And this comes from the fact that within the ocean column, you will have different temperatures. So it's a layered structure, the water column. And because of the different temperatures, the waves, they propagate with the different speeds, and creates this kind of propagation where you have the dead zones where no signal is received, and then you have zones with very intense signal reception. So if you were to position a receiver around this area where it is dark blue or down here, it's very likely you will receive any signal because of this phenomenon. For the other channel, as I said, is the shallow water, which is more applicable for people that don't have a lot of money. So it's a big issue to go and deploy at even at 1,000 meters. It's a quite expensive operation. So for most research, I think is done in the shallow water channel, so that is less than 200 meters, and you can see in this case the sound speed profile is very constant, so it doesn't create those wavy propagation curves. So that's a typical propagation if you have a 40-meter channel, and you can see you have interactions with the sea surface and the sea bottom. So up to 2,000 meters in distance, horizontally, you can manage the transmissions very nicely. So this was recorded from some experiments I did in the North Sea. So that's off the coast of England, facing France. And in the summer, typically when you go for experiments, the profile behaves very nicely. So most of the research in this area is done for shallow water channels, and there's some research for deep waters, but the majority is for shallow waters. Okay, so what kind of problems you get there? Yeah, the first one is the signal to noise ratio. You know, this is a very critical parameter for communications. So I have included also the interference here. So it's signal and interference noise ratio. So typically, if you add all of the interference and the background noise, you get a signal to noise ratio which is less than 12 dB. So that's one of the problems. So it's the signal goes below levels that you can have meaningful communication. So you have to find techniques to overcome this, like using an array of receivers. And then the bandwidth is very limited. Yeah, so typically you would get a bandwidth between 8 kilohertz and 40 kilohertz for if you want to reach maybe up to 10 kilometers. And then after that, the bandwidth goes down very, very rapidly. We have also what we call wideband signaling. Yes, so imagine if you operate in this range and the carrier frequency that you're using is only half the bandwidth, twice the bandwidth, then you get these problems with wideband signaling where you have a lot of multipath present, and also the Doppler kicks in and has a significant effect. Yeah, so these are the key effects. So you get from wideband signaling the multipath spread that we call is very long, could be up to 100 symbols. So this gives rise then to what we call frequency selective multipath. And on top of that is a very hostile environment. There's a lot of movement, so you get Doppler and the Doppler um, is not similar what you would encounter in wireless communication. So in wireless communications, you will get a rotation of the constellation. So that would be what the Doppler effect would be. But for underwater, what you get is a compression and an expansion of the actual signal waveform. So it's much more significantly. So you get the rotation of the constellation that you transmit, but also you get a compression and an expansion of your symbol duration. So before you can do any demodulation, you will have to address these two effects, yeah, the long multipath and the Doppler spread. And there's also system-related limitations. Yeah, so the cost, you have to make everything waterproof, and they have to go, if it's shallow water, for example, they have to be able to withstand pressures of very high water pressure. And then there's also cost of deployment. Sometimes the cost of deployment is higher than the actual equipment. Yeah, so imagine if you have to deploy somewhere in the world the equipment, then you have to navigate there and travel physically there and deploy. So this cost sometimes is like 10 times the actual cost of the modem. Yeah, so a modem, you can get it between, I think it depends on the company, but you can get a modem with 20,000 pounds sterling, yeah? But the actual deployment in the ocean could be 100,000 in terms of cost. So these are all costs, the lifetime of deployment. So if you have a deployment somewhere in the ocean, you don't want to frequently go there and change the batteries for your modem. So you want your modem to last at least 3 years is what the recommendation from the oil and gas company comes. So you want the whole system to be able to operate for a few years before you need to consider changing the battery. And so when you design this kind of modems, you have to find a balance between how fast you want to transmit and what the power consumption is. So if you want to last for 3 years, then maybe you need to reduce the requirements for the speed of transmission. Yeah, and there's also another balance between transmission speed and range. Yeah, the higher you go in speed, the more bandwidth you need, and the attenuation then kicks in, and then the range you can reach is not as long. Yeah. And there's also issues with transmission latency. So if we use acoustic wave, it takes physically a few seconds for the wave to propagate from A to B. And in most cases, we use half duplex. So that means like when you transmit, you cannot receive because the local receivers are all blinded by the strong transmission signal that you send out. So you have to wait almost half the time until the signal has gone out, and then the other node can transmit and receive. So we call this half duplex. And fouling, of course, yeah. So fouling is a big problem. So you put something in the water, in a few days or a week, there would be living organisms on the modem itself. I will show you some picture next. Yeah. So fouling is also a problem if you want to deploy something long term. So that's a summary of what I have discussed so far. So this is a typical shallow water scenario. So you have an AUV, an unmanned underwater vehicle. So it moves typically around 10 meters per second in either direction. And we have the uplink, which is the most challenging one. So you send signals from the AUV to the research vessel, and the signal gets a direct path to the receiver, but also gets these reflections, which cause what we call the multipath propagation problem. So typically this link is up to 40 kilobits per second. And then you have the downlink, which is around 100 bits per second. So the demand is very low for data rate there. But it has to be very reliable because you send instructions to the AUV to maneuver and navigate. Depth, typically for shallow water, 200 meters. Range, maybe less than 3 kilometers, but if you can extend it to 10 kilometers, that's a plus. And so you get these reflections. The reflections from the sea bottom are very stable because the ground doesn't move a lot. So that's more easier to deal with, like compared to the reflections you get from the surface, because the surface itself is a very dynamic environment. So you have the waves, and the crest would be in a couple of seconds in a different place, and so on. And of course, you have the noise that comes from the ship, from the environment, from drillings in the area. So that's a typical scenario. And of course, if you want to improve your scenario, you will use multiple hydrophones for your receiver array to improve the signal reception. So typically, you have this kind of scenario that you want to implement a robust communication link. So if we look at some of the impairments, that's the first one, is the signal attenuation. Yeah? So this is a problem from nature, so we can't do much. We can only increase the transmission power. Yeah? So if you look at the overall attenuation, so I have here the attenuation per kilometer, yeah, so dB per kilometer, and here the frequency. So it's very frequency dependent, as you can see. And the higher you go in frequency, 10, 20 kilohertz, the overall, this blue line is the attenuation per kilometer is very high. And this attenuation is composed of these three effects. Yeah, so you have the manganese relaxation, the boric acid relaxation. They all contribute to the overall attenuation. Yeah, so this attenuations is they capture how the molecules can oscillate. Yeah, so if you go higher in frequency, there's some saturation, and then you get these high attenuations. So this formula, you put it in the well-known signal-to-noise ratio, and you can work out what is the expected attenuation eventually that you will get. Yeah, so you have, for example, this other. So that's how high you transmit. That's the attenuation. That's a loss, and then you have to subtract also the noise, and also. So this is done for a single frequency, so you have to subtract your bandwidth as well. Yeah. So that's typically what we deal with, and that's if you work out for up to 3 kilometers, you can get maybe just around 10 dB of signal to interference and noise ratio. So it's not a very high SNR situation. Yeah. So we have to deal with a lot of ambient noise. So that's how the noise looks like. So the noise itself, so that's a man-made noise. So if it's near the DC, it's very high, and then it goes down with frequency. But this also can cause saturation on your receiver. So these recordings are from our 8-element array. So that looks like this. So sensor. So the hydrophone one was on the near the bottom. So that's what you record on the bottom. It's a bit less noisy at the bottom because the man-made noise gets longer to arrive to the hydrophones near the bottom. And this is the hydrophone near near the sea surface. And the spectrum of this signal then is shown here. As I said, there's like strong contributions of the noise around the DC area. So typically you will not operate here because of that. So you will go above at least 5 kilohertz in terms of where you set your carrier frequency. So if I show you maybe when we did this experiment, we sent a diver down just to show you what a couple of days of fouling does. So that's the array itself after a few days inside the water. So this is the horizontal section. And you can see already in a few days, there's it's almost covered in jellyfish. And imagine if you leave that for a year or 3 years, it would be completely unrecognizable. Right? And so that's the cross section, and this is the vertical elements. So this is a transducer optimized for around 12 kilohertz, and ideally you don't want to use an array because it's very difficult to deploy and very difficult to manage inside the water if there's currents and so on. And I have also the recordings just to show you how the sound sounds like inside the water. So this is the noise. One is near the bottom. So that's the static background noise without any signals. And you can hear this high frequency noise is the waves splashing and creating this splashing sound. And so that's for the sensor down close to the bottom of the sea. And this is the one close to the sea surface. You can see the high frequency effects are more prominent here because they are very close to the source of that generates this kind of noise. So that's near the sea surfaces. Yeah, but you can have also artificial type of noises depending on which area in the world you are. For example, if you are close to Australia, there is like a shrimp noise, like this one. So this is something you cannot deal with. So you have to deal with this using signal techniques. Yeah, so you cannot do much if there's wildlife in the water. That's a dolphin. That's for example more. This one, because it's within the frequency normally that we transmit, is more harmful. Yeah? So all these noises create interference to your signal, and they can get your beta rate, for example, to very high values because they are within the signal of interest. Okay, so and then if you look at the signal itself, this is how it sounds. In this example, the signal is operating while you have the boat engine on. So that's a typical signal transmission. Yeah, you can hear the periodic chirping. I will discuss what the chirping is next. So we have then this. So that's the signal plus the boat noise plus the environmental noise. Yeah, but you can have also drilling in the area. You can have all sort of problems. Yeah. So that's the array. If you can afford an array, of course it's welcome. But as I said, it's very difficult to deploy in the water and maintain. And it's also more expensive, yeah, because you have multiple hydrophones inside. I think one hydrophone is around 2,000 pounds in UK money. So if you have 8, you have eightfold the cost. So ideally, you want to have a system that has one transmitter, one receiver, and you can get away with the SNR and the quality of the reception. Yeah, so that's a typical two-user system. This was recorded in the North Sea in UK. So you can see that you have one user at 3 kilometers, that it's this transmission. And then you are 1 kilometer closer, the transmission is much stronger, yeah? And this is where the transmission start for user 1 and user 2. And we have used a very strong transmitter for this experiment, up to 192. The unit is relative micropascal for this type of acoustic transmitter. Okay, so in terms of modulation, we use standard modulation that come from the wireless environments. The highest normally you would go is up to 16 QAM, and then the SNR is not high enough to go higher. But the most reliable ones are the QPSK. Yes. So the QPSK is like a 0 and a 1 quadrature area. 8 PSK is also worth considering, and it's a bit better than 8 QAM because the envelope is constant. So if you need to use 8, 3 bits per symbol, I would recommend the 8 PSK. And I have here as a reference the bit error rates for these schemes. Yeah, so BPSK performs the best in terms of bit error rate, but it's very slow. So this is for the AWGN channel, but it gives you a reference. If you have multipath and Doppler problems, it will become worse than this, of course. And this is also uncoded, yeah. So you can see BPSK is the best. Typically, 10-3 is a good uncoded bit error rate, and then you can use your coding, your error correction to remove the error. So 10-3 means it's 1 error in 1,000 bits, and that's easily correctable even with a very high rate error correcting code. So for QPSK and BPSK, we have this point here, which is important. And most modems you will use QPSK because it's quite robust. If you are short distances and you want a bit more data rate, then you can consider also 16 QAM with some sort of coding as well. So this is the typical modulation formats that most modems that you can buy will use. And everything, because of the low transmission rate, everything can be done in a microcontroller or a DSP. So all the algorithms that you will develop in this area will be run in a DSP. And at the end, you will have a power amplifier that sends the signal to the transducer. So the transducer will normally be inside the C. Yeah, and your data, it comes from whatever you measure or from your instruments. And typically you will apply an error correction code with some sort of interleaving to give some diversity in the data. And then it will be modulated to one of those formats I presented, QPSK. And after that, you will have pulse shaping and IQ mixing to get a real valued signal that goes then into the power amplifier. So once you have the data would be 0 and 1s. Then what you will do is like apply the error correction and then give a shape to your waveform. So because you cannot transmit a single 0 or a 1, you have to give it a waveform in form of a shape. So the shape then gives this sync type of spectrum at the baseband. So that's still located at the 0 hertz. And typically, because this energy is wasted if the transducer cannot respond to very high bandwidth. So typically we apply pulse shaping. So we limit the energy within the response of the transducer. Yeah, and in the last step, we shift the frequency to whatever the optimal frequency of the transducer is. Yeah, and you can see this effect when you have pulse shaping. There's no energy wasted outside the frequency response of the transducer, so it's much more efficient. Otherwise, if you have this type of signal, the transducer won't be able to respond, and the signal will be converted to heat. Yeah, so you're just wasting energy there. So it's good always to have this type of pulse shaping for your waveforms. And so that's how a transducer looks like. So this is the typical impedance. Yeah, so impedance can be translated also to what you call it, bandwidth efficiency. So transducers normally they're used for transmitting, so they are optimized to handle large values of large voltages. And the receiver is a bit more delicate, and you can have also a very wide band transducer that goes back to up to like maybe half a megahertz if needed. Yeah. And these are the most costly elements of a modem, and along with the waterproofing and pressure proofing of the modem enclosure. Yeah. So this is from the practical point of view how you implement. So in practice you have to deal with two effects mainly. Once you've dealt with the attenuation and you supplied enough power to your signal to reach the receiver. So once you reach the receiver, you get this multipath propagation effect. And so it's nicely demonstrated here. So you can see, so you have rays that reach the receivers straight without any reflections, but you have also a signal that reaches these positions via the surface or via the bottom reflections. And this creates what we call the multipath propagation effect. So effectively the same information arrives multiple times. Even when you finish with that symbol that was transmitted and you transmit more symbols, after a while you will have a reflection that comes from the past transmissions. Yeah, and this creates a big problem that you have to remove it before you do any recovery of the information. So from practical point of view, you model this as an FIR filter. Yeah, so where you have these weights here representing the amount of the reflected signal that arrives at the receiver, and these delays represent the actual delay in the propagation. Yeah, so if you look at this plot, so the signal going to the surface and coming down has a longer wave, longer way to arrive to the receiver than if you go straight. Then this is reflected to these delay times. And eventually, if you put all together, you have this, what we call the impulse response of the channel, or the CIR, where you have the actual attenuation of the channel. You have also a rotation because of the delays. And you have also this delay in the path that is time varying. So once you add all this together, pass your signal through this type of model, you need to add also the background noise, and that would be the model for your received signal. So if you do simulations and you have practical measurements of channel, this is a nice model that you can apply for simulating without getting wet your communication link. So how do you measure now these coefficients? So typically, if you consider a frame of transmission, you will have packets with data modulated. Yeah, so I have here from packet 1 to packet n. And at the start and at the end of this packet, you will put a chirp. So a chirp is like a swept sine wave, but it has very good Doppler properties. So it's very Doppler tolerant. So this is what dolphins, for example, or whales use because of that. And you can use then correlation at the receiver to find out the profile of your channel, effectively the CIR. So because you know what chirp was included at the transmitter, so you can regenerate that signal locally at the receiver and correlate, and then the correlation will give you the impulse response. Yeah, and we also add this silent period between the chirp and the actual data, so that the chirp doesn't spill over to the actual data. So here within the packets, we only deal with interference from the packets themselves and not from the chirps. Yeah. So that's why we typically add a silent period of around 50 milliseconds. That would be the max if you have a very challenging channel. So you send then this signal and you receive it. And so this is a typical experimental setup. You will try to put your transmitter as deep as possible to avoid interactions with the CSAR phase, but the receiver can be very close to the CSAR phase. So I have an impulse response recording here just to show you how the impulse response varies with time. I don't know if the delay or the latency in the link here will cause any problems to see it. So that's a typical variation in the multipath profile, and this was detected using this chirp approach. And you have some multipaths appearing and disappearing because of the way the channel dynamics work. And so this is the key information, and all these paths are reflections from bottom or the surface of the sea, and this is what caused the intersymbol interference. Yeah. So so if you plot this in 3D with time, you get this plot where you can see that's your main transmission, which is also time varying, but you also get the multipaths that are time varying, and you can see the propagation over the time. So this particular channel has a spread of 50 symbols. It means like the current symbol that you are receiving causes, for the 50 next symbols received, it will cause interference. And typically you have to have a measure at the receiver that removes these multipaths, either in form of the decision feedback equalizer, if it's single carrier transmission, or if you are using OFDM, you can use the actual FDM itself to avoid the multipath. Yeah, so how do you measure this? So typically you would measure the RMS delay spread. Yeah, so this is the well-known variance formula. So you remove the mean propagation, and then you perform this equation. So you compute the variance of the spread, and once you know the RMS delay spread, you can also find out what is the coherence bandwidth here. So that's the inverse of the RMS delay spread. That gives you how stable is the frequency band if you look at this in the Fourier domain. So so that's if you look at the 3D from the top, from the 3D plot. If you look from the top, that shows you the variation of the channel. So that's the short variation over 2 seconds. But if you look at over 20 seconds, you can see also these drifts because of the experiment. If you remember, we have this experiment, and if the boats are not anchored, then they drift with time, and you can see here the drift from the experiment. So it's not significant, but over if you do the experiments over an hour, you can drift significantly with the car, and then that can cause synchronization problems. So that's the multipath variation, and that's if you take the multipath profile and you look at this in the Fourier domain, you can see the coherence bands, which is how stable the frequency bands are. Yeah, and in this case, from these measurements, we worked out the coherence bandwidth to be 263 Hertz. So it means like every band of 263 Hertz receives the same attenuation. But you can see as you move along to the whole bandwidth, you get these frequency selective effects that need to be considered when you design the system. Yeah, and the other key problem is the Doppler. So this is when you have moving vehicles, especially. So what we call Doppler spread is, in fact, a signal dilation. And dilation means your waveform is expanded or compressed depending on the direction of movement. So if you have an AUV going into this direction, and another AUV going faster or slower into this direction, then you'll get the signal expansion. But if the other AUV moves towards the first AUV, then you get a signal compression. So effectively, if you design your system to have a specific duration x, when you have an expansion, it would be x plus something, so it's longer in time. But when you have it in the other direction, it would be shorter in time. So these formulas here give you the relationship between the new carrier frequency. Yeah, so the carrier frequency is also shifted in this case. So it depends on the speed of movement. So that's the difference of the two speeds. So it's the absolute value of the difference. And that's the actual speed of propagation of the acoustic wave. And also the timing is changing, yeah, because of that. And you get either a compressed waveform or an expanded waveform. And both these effects, the multipath and the compression or the dilation, they need to be removed before you can do anything in terms of detection. Yeah, so that's the equivalent of the Doppler spread. So that's how the main waveform, the main arrival changes with time. So if you look at this also in the frequency domain, you can see that it's subject to fluctuation, and you can work out the Doppler spread from this. So now if you have the RMS delay spread and the Doppler spread, you can work out whether you will be able to use coherent communications. Yeah, coherent means like you can recover the phase, and if you use like QPSK or BPSK or even QAM, information is decoded in the phase. So these two parameters will tell you whether you can use coherent communication. So from this one, from the coherence time or the delay spread, we can work out the spread factor. And the closer this factor is to 1, the worse the channel is. And so we want it to be ideally very small, so that we have what is called underspread channel, and then we can use coherent communications. So it depends, of course, on the application. Yeah, so if you have like civilian applications, maybe it's not a big problem. But if you have, for example, communications between a Navy vessel and a torpedo, then the Doppler will be very high, the multipath spread will be very high. So you need to use very specialized schemes in this case to avoid the coherence of the channels. Yeah. So that's from the design point of view. So typically, if you have Doppler, the way you correct it is using the information that you get from these chirps that you include in the signal waveform. So by design, we will know the transmitted duration. Okay, so this is by design. We can work it out based on the duration of the silent periods, the duration of the chirps, and depending how many packets you have. So on paper, you can derive this number. And then once you measure from the correlation how far these peaks between the two chips have progressed, they can be the duration can be shorter or longer. So from this new information that you get from the received signal by correlating, you can work out whether there was a compression or an expansion. Okay. So you get the ratio and you subtract 1 because of the duration itself, and you can work out how many samples your new waveform is longer or shorter. And then you know what you have to do in terms of decompression to remove the dilation. Yeah? So at the receiver, you will have synchronization. So this would be the correlation, yeah? And then you get the synchronization starting point. And you will use an interpolator to either make your signal longer or shorter to counteract the effects of the dilation. Yeah? And once you remove the Doppler, then you go into the multipath removal so that you can remove also the other effect. So when you do your detection, after you receive your signal, the first thing you have to do is like remove the Doppler and then remove the multipath. And typically at the front end, you will have this operating. So from the hydrophone, you will go to a preamp to amplify a bit your signal, and then you will digitize and apply a bandpass filter to isolate your signal of interest and avoid out-of-band noise in this case. But all of this receiver will be an implementation in digital form on a DSP or on a very fast ARM microcontroller. Okay, and from this duration, yeah, we can also work out what the resolution in terms of Doppler we can get. So if you plug in your bandwidth and the duration of the signal, then you can find what's the smallest Doppler that you can remove with this method. So first effect you remove is the Doppler. So you try to correct the sampling frequency and timing that was introduced by the Doppler. And there's different methods that you can use. For one was the one I presented here with the correlation. But you can use linear interpolation, you can use FFT-based interpolation, you can use interpolation and decimation. So there's various methods that you can use. It's a bit beyond the talk. So that's one example of what happens if you send a sinusoidal signal and you have a Doppler. Yeah, so if you have expansion, then the signal would be moved to the left of your carrier. So that's the original carrier without the Doppler. If you have compression, it will move to the left of the carrier. And then if you apply the method I mentioned before with the correlation, then you can get the carrier and the timing to the right position. So this was a bit exaggerated just to show you the effect. So 10% Doppler is really very high. So normally you will talk about maybe maximum 2-3% Dopplers for a practical system. Yeah, but because on MATLAB or Python you can do that and stretch the limits, then so that's just to illustrate the effect. Okay, so that's a typical receiver that deals with both effects now. This was implemented in a modem that we developed when I was at Newcastle University, and that's the type of transducer we use. Is a piezo type of transducer. The cost of this one, it was optimized to be below $50 total. Yeah? And if you mass produce it, it could be much lower. The idea was to have an Internet of Things type for underwater stuff. So we developed this to last over 3 years and also be compact. So you can see the scale is not very high. So this will be integrated and you'll have the modem and the actual transducer in the same package. Yeah? This is the first part is where we deal with the Doppler, and the second part is a typical decision feedback equalizer. So this filter will remove some of the multipath, and then once you detect the signal, you will remove the remove future symbols from your signal too. So the whole thing is optimized using a mean-square error type of optimization of cost function. So all these parameters for the filters, for the Doppler, will be subject to this cost function. And eventually, once you take the derivative of this cost function with respect to the individual parameter, you can find solutions that are iterative, and it works very well. Yeah, so we could get up to 40 kilobits per second with this type of receiver. And the error is then built between. So you have a decision device here that builds this error, and typically you will have two modes of operation, one where you train your receiver and one where you detect. Yeah? So that's the typical digital receiver. And as I said, although it looks like blocks, they are all algorithms implemented inside this ARM-based receiver. Yeah, and that's a typical performance example where you get this nasty impulse response. And if you don't do anything, this is the constellation you will be receiving. So it's there's no way to discern what modulation is. It's very, because of the multipath and the Doppler, it's very difficult to do any reliable detection. Yeah? Now, if it works fully, then you can see QPSK was transmitted and the SNR was around 16 dB, 16.5 dB after you remove all the multipath and Doppler effects. This is a typical convergence for this error signal.
Now it's good only. For you don't have any problems, you can go to
17 not good.
1.65 lakh.
Is there any issue?
कोई वगैरह से आते हैं ना
1 lakh नहीं लगता.
Okay, so that's a typical example, as I said. Let me continue. So once you operate fully with both Doppler correction and multipath correction, everything works nicely. So if you disable, for example, the Doppler correction, you can see the carrier is rotated, that results in rotating the constellation. Although you can still see it's a QPSK constellation, then it's still not optimal as this one. Yeah, so this one gives you error-free reception, and that's how the Doppler interpolator works. So from the Doppler also you can get the speed. If you subtract one and you multiply with your sound estimate, speed of sound estimate. And then you can see for different directions here what the estimated SINR is. So it can handle directions in both both expanding and compressing. Okay, so this is in terms of if you want to do research in this area, what is left to do? Yeah, so currently there's a need to push the data rate from 40 to 50, from 40 and 50 to 150 kilobits per second. Yeah, so that's an ultimate goal for acoustic communications. There's work to do realistic modeling on the channels, so that you don't have to go to the sea to do the experiments that are very expensive. You can do work on communication networks, how you set up your startup protocols, and you can do cross-layer optimization. Dense network, if you have many nodes using what is called Internet of Underwater Things. And optical communications, so this is where the quantum bit comes in. So it's typically reserved for short ranges because of the effects I will discuss. And you can do research on the receivers. Yeah, you can combine, for example, coding schemes and Doppler correction and multipath correction. So these are typical research themes that you can still do. Yeah, so you can look at Doppler correction and multipath correction separately. There's work now going on multi-carrier systems. Yeah, so this comes from the advancements in 5G and 6G. So you use OFDM with coding, and you can derive improved performance. Yeah, so I'm not gonna, I think, in the interest of time. So I will go a bit quicker now, just to arrive on the quantum stuff. So we have the multi-carrier system. This comes from 4, 5, and 6G. So instead of transmitting at a single frequency, in this schemes, you split the transmission in smaller bandwidth transmissions, and then you add them all up to create what is called a multi-carrier signal. And the benefit is that you can apply coding to get diversity, and you can also get receiver structures that are less complex, and lower complexity normally translates to longer battery, and that's very important for underwater. Yeah, so you can use techniques that are applied now in wireless comms. Yeah, like first you get resilience to multipath, and then you have the simplification for the receiver, which results in better battery lifetime. And then you have also other effects that you can use bit and power loading at subcarrier level. Yeah, for example, if one subcarrier band is very bad, maybe you can even exclude it from the transmission, and this is called bit and power loading. So selectively finding subcarriers, for example, that are not performing well, and exclude them, or load them with less lower modulation orders. Yeah. So that's a typical transmitter and receiver for the multipath. It's a completely different approach compared to single carrier. At the receiver, you only need to do moderate equalization, but this multi-carrier system, they have bigger problem with the Doppler. You still have to deal with the Doppler. So Doppler correction, this is another scheme for Doppler correction for OFDM type of signals. If you know OFDM, you have what is called a cyclic prefix included in the OFDM waveform, which is the end of the signal is copied also at the front of the signal. And because of this redundancy in the waveform, so you have the same information here and here, you can do correlation with with a specific delay or a correlation lag. It's appropriate word for that. So you correlate at a specific correlation lag, and then you can find out the correlation function based on the cyclic prefix. Now, if the correlation function is not shifted, it means you have no Doppler. If it's shifted right, you have expansion. If you have a shift to the left, you have compression. And based on this information, then you can resample the waveform. Yeah, so that's feasible because of the presence of the cyclic prefix. Yeah, and that's a result, for example, with a very moderate speed and acceleration. It works very well. So the blue one is with no Doppler, and then you have expansion and compression on left and right side of the correlation line. So that's research on the multi-carrier system. You can have also research on multi-users, so you can operate users at the same time. Yeah. So this goes to what people were using in 3G. Yeah, but it's still a reliable solution for underwater. Yeah, so you introduce what is called a spreading waveform. So instead of sending simple duration symbols, you expand the symbol into a waveform, and then you create a time diversity like that. And you can, if you have this type of waveform, you can afford to have interference from other users, because when you do the correlation with the waveform at the receiver, the actual interferers, they are removed. And for this type of interference-based system, you will use for your waveform what is called the goal code for spreading. And this gives you a very high peak when the codes are aligned, and a very low peak when the codes are misaligned or the code is coming from another user. Okay, so that's the state of the art. You know, I think the best modems you can get now are around 50 kilobits per second. And this is where quantum comes in. I must say there's not a lot of research in this area. It's just starting now. So if you plan to do any research, it would be pioneering, let's say. So for this type of application, you normally use an LED, and the wavelength would be either blue or green, because there's a window in the light spectrum where it's transparent in the water. Yeah, so this is between 450 and 550 nanometers. So your source will come from the blue-green window of the light spectrum. And this is typical also for the classical laser communications that you can do in underwater. So there's existing research, but not at quantum level. It's more like optical communications. And but the same principle can be applied also to quantum photonic links. And one benefit that you get is you get very high bandwidth. And you get additionally the quantum level security, which is not present if you have just the optical link. The drawback is that because of the sea environment, you can only use it for very short ranges. Yeah, and the environment is very challenging. Yeah, so there's some effects that I will discuss next that prevent long ranges. But because of that, you maybe combine the quantum links with acoustic links or satellite links to achieve like a hybridized version of quantum and acoustic. So that's the scene for quantum comms. So if you look at the typical optical communication, yeah, so I have a plot here where you see the distance versus what speeds have been reported to be achieved. Yeah. So for underwater, you can you can reach very long distances at very small rates. And as the rate goes up, the actual distance is reduced, and the threshold where you can start using optical communications is around 80 meters. So after 80 meters, you can reach very good speeds with underwater optical communications. And you can go up to 1 gigabit per second for very short links at 1 meter. And this is a useful application if you have, for example, a submarine docking and you want to update the software or you want to exchange data from the trip. Then with this kind of link at 1 gigabit per second, you can have a very short optical link where the communication happens. Yeah, but anything above 100 meters, the optical communications will fail. And this means that also if you rely on the quantum on optical links, they will not be very good either. Yeah? So we are looking maximum of 80 meters in distance and probably very good speeds, yeah, for the underwater applications. So that's the starting point. So don't expect hundreds of kilometers eventually using quantum links. And the problems are these. So you have once you transmit your light, so it will attenuate very quickly in the water. So the range would be limited to a few tens of meters at best, yeah. And it's not just the attenuation, it's the water clarity as well. So we are not talking about clarity that you get in a glass of water. So these are very dirty environments. Yeah, you can have currents with sand flying in the water and so on. So it's not a clean environment. So and that affects the propagation of the photons. So you get because of that reduced signal strength. Another problem is the dynamics. Yeah? So inside the sea, you have a lot of dynamics. The optical links, unless you moor them or anchor them, they would be also moving with the sea water column. So it would be difficult to maintain the line of sight. So even with small misalignments, they can bring off the communication link. So you have to have some sort of tracking. And then there's also the environmental interference. Yeah. So if you're operating a link during the day, there's the sun. There's also fish that produce light inside the water. So all these are interferences for the actual communication link. So these are some of the key impairments that prevent the signal going into the distance. And also from practical point of view, if you have movement, you have to have very precise tracking. So that's the challenges to overcome if you want to have a good quantum link. So you have to deal with the absorption, the scattering, and the turbulence. Yeah, and so you need to have a way of preserving the quantum states in these harsh environments. Yeah, and the last one, which is not necessarily related to quantum, but still important, is the alignment and tracking. Yeah, so somehow they have to be linked, the transmitter and the receiver, to optimize the link. Yeah, so that's some of the challenges that you have to overcome. In terms of applications, the most popular, I think, is the secure quantum key distribution. So if you overcome all the challenges that I mentioned and you establish a good quantum link, so then you can use it for encryption, yeah, and the receiver measures typically the photons that you detect. And you can also use an acoustic link to exchange information about what kind of measurements you have received without revealing anything from the environment itself. Yeah. And then because this security is based on the law of physics, it's very difficult to crack. So they are not crackable with brute force kind of computations. So there's information encoded from the environment that it's impossible to use brute force to break. So that's one of the key applications and most popular. And the other one is not very active at the moment, but I can sense this coming. Is the quantum sensing and imaging. Once you use the photons, they will be very sensitive to the environment. So if you can remap the disturbances back to the actual channel properties, you can do like a very accurate sensing and imaging. Yeah. So you can get a precise modeling for the environment, and that means like you can detect what the environment is itself. And so this, if you can manage this, you will get very cutting edge sensors that can map oceans or detect objects underwater and so on. So that's the second most appealing quantum related application. And then the last one is navigation. Yeah? So for navigation, currently the submarines, they use inertia type of sensors. And if you are underwater for a very long time, then you don't have the GPS update to recalibrate your position. So if you were to have ultra precise quantum accelerometers, so effectively gyroscopes that rely on quantum states to get information about the inertia, then that would lead to more secure sensors. Yeah, and if you combine this with the SQKD, then you will get enhanced navigation security for your navigation, and also higher accuracy and stealth. Okay, so that's the quantum bit. I mean, as I said, there's not many research works in that area, and we are starting to do some work with the underwater transmitters for quantum. And this concludes the talk and all the stuff I wanted to say for today. So I'd like to thank also some of my old funders. Yeah, so they funded some of the work I did in this area for over 20 years. Some of them led to products, like this one is the modem I showed you, with the low power and low cost. Yeah, so thank you very much, and I'll be happy to take the rest of the time for if you have any questions. I will stop sharing my screen now.
First of all, Harris, Sudeep here. Thank you so much for the presentation and the talk.
You're welcome.
So participants,
if you have any questions, do ask now, but you can, I mean, if it's a longer question, you can take it offline, and send me an email, and I would be happy to converse with you online.
So participants, do you have any questions? Yeah, I think Dr. Kamlesh has raised his hand. Please unmute yourself and please ask a question. Dr. Kamlesh. Dr. Kamlesh, we can't hear you. Please ask a question. Yes, Dr. Kamlesh. Please go ahead. Don't think we can hear Dr. Kamlesh. So anyone else would like to ask?
Maybe he can type the question on the chat, and if we can.
So you can type the question on the live chat, if you can. or if anyone else has any question. Okay, I think we don't have any questions. So in that case, so if there are any questions, you can also type your questions to me and in the feedback form. So we'll take those questions and pass it over to Professor Harris. And as soon as we get our reply from him, so we're going to share it with you. Okay. So Harris, thank you so much.
Okay.
It was lovely to have you, and hope to see you again. And regarding our Spark project, I hope that I don't know. Have you made any plans to come over to India or no?
You know, health-wise, I'm not really. I had some problems with.
Yeah, you mentioned.
And I mean, the doctor advised me not to take. I mean, it's a bit hardship to travel for many hours, you know, for me now.
Yeah. So is Shahid in the UK or is he in Portugal?
He's in Portugal. I don't know if he plans to come, but we still have a window that we may come, you know.
Yeah. So it's still March. The project runs till March. So I'm also planning. Yeah. I'm planning to come around December. So let's see. But means I'm planning, but with all the teaching and research and all, sometimes it becomes difficult. But yeah. So if not this year, maybe next year, surely in ICC. It's happening in Glasgow, right? So I'll definitely by that time the project would be over, but
well, it doesn't matter. We may get the new project.
I'll get to see you guys. Yeah.
Sure. Thank you for the invitation, and it was a pleasure to to give you this talk. Hopefully, if I interested you in any of these topics, maybe we can have even a collaboration. Please, my email, I guess it's easy to find on the web. Just contact me directly, and we can have a
I'll also share it. I'll also share with the participants. And Harris, could you please share the slides, if not all, at least a snippet of it, so that I can share it with the participants?
Sure. Yeah, I can. A PDF would be okay.
Yeah. PDF is great. PDF would be great.
Okay, so it's about 4 megabytes. I don't think it's a problem.
No, it's not a problem. It's not a problem. And also, Harris,
so I'll send you an email with the slides, and then you can circulate them.
Yeah, means along with the slides, it also means at the end of this workshop, we also have a quiz for the participants. So if you could give 5 MCQs, so that would be great.
But where is the quiz?
So the quiz is on Saturday. The quiz is on Saturday after the workshop ends.
So you will let us know some instruction on how to fill it in, yeah?
So I'll send you an email. I'll send you an email requesting 5 MCQs.
Okay. Thank you very much.
Yeah, great. Have a good evening. Bye-bye.
Bye-bye.
So thank you everyone. So it was a pleasure meeting you all, and I hope you enjoyed the workshop till now. So I wish you all a very good night, and I'll see you again tomorrow. Bye. Have a good night.